part of this unit. Everything that you've done so far in this particular unit is going to be used in the next unit where, okay, we've learned about how to heat up a specific material. Now we're going to talk about what happens if two materials come in contact with each other. How does that heat get passed on? Okay, but today we're talking about total heat. And I mean, basically, if you think about it, total heat means total heat. So we're going to look at total heat as equaling the sum of the specific heats and the sum of the latent heats and adding them together. Okay, and when I say them, because you think, well, okay, there's only one specific heat, and there's only one latent heat. No, there are many of them. Okay, so with an object, okay, if you freeze something, right, or make it solid, you can bring that temperature down farther, right? And at that point, you're using specific heat, right? You're removing heat and cooling it off, but the the shape, the fact that it's solid isn't changing. Okay, then you meet that section where it's either going to freeze or it's going to melt, right? Temperature's not going to change, but the phase of the material will, the state of the matter. So if we're going upward, that solid is then going to become liquid. Once it's all liquid, then you can warm it up, right? And you can warm it up all the way to its boiling point. When it boils, it stays the same temperature until all of it becomes a gas. Okay, so during the boils or condenses section, again, there's no temperature change, but it's going to start as a liquid. Okay, and then throughout that time, all of the substance is going to turn into a gas. Once that has happened, then you can superheat it so that you have super hot gas. Okay, so there are 1, 2, 3 possibilities for the specific heat, and there are 1, 2 possibilities for the latent heat. Okay, so in this example, we have Superman, and he's vaporizing a 1800 kilogram ice monster with his heat ray vision. The ice monster was at negative 20 degrees Celsius, right? Takes a lot of coldness, right, to keep that monster together. Okay. After being vaporized, he is steamed at 135 degrees Celsius. How much energy did Superman expend? Right? So how much did he transfer to the heat monster? Okay. So we know that we're using an ice monster, right? So we know that we're using water. We know that the specific heat of ice is 2090. Again, that would be given to you. Liquid water is 4,186, and steam is 1,970. Okay. For water, the heat of fusion, or LF, is 3.3 times 10 to the 5th joules per kilogram. We've talked about that one before. And then the heat of vaporization is 2.26 times 10 to the 6th joules per Kelvin. Okay, So you'll notice that to vaporize something, you need a lot more energy. Okay. So what we're going to do is we're going to separate each of the sections, right? So from -20 to 0, the temperature rose 20 degrees. Okay. And the specific heat at that point was the ice. Okay. Then it has to go from ice to water. So that's our latent heat. We're going to use the latent heat of fusion. Okay. The next step is to go from water and to the boiling point, right? Raise the temperature of the water to the boiling point. So that's where we're going to use our specific heat of water. And then our temperature is going to go from 0 to 100 degrees. The next step is changing all of the water into steam. Okay. And then that steam, right? That vaporization, we're going to use the latent heat of vaporization, right? The next step is we're going to superheat, right? So we're going to use the specific heat, but this time of steam, and then the change in temperature. We're going to take each of those and calculate them and then add them all up. So when you look at this actual problem, the answer is 5.62 times 10 to the 9th joules. Okay, that is a huge amount of energy, right? But it's not unnormal for heat energy. Heat energy has a lot of energy.